Alright folks, today we are going to review some from the video you watched last time after the test, and then also cover one small thing regarding the multiplication counting principle. Okay, so the set notation was referred to a little bit last time. We are given two sets here, A and B, and it gives us some numbers for each, and we're just going to take this time to review what each of these symbols mean. So this U is familiar from domain and range. Okay, that means union. And regarding English words, that's going to look like an OR. This second symbol that looks like an N is AND in English stuff, and it means intersection. So when we read this out loud, the first one says A union B, the second one says A intersect B. And what we're going to do for a union is just look for anything that is A or B, meaning listing all of the things in A, then combining them with all of the things in B without repeating ourselves, just like when we talk about domain of discrete sets. So start out, just list all of the things that are in A. Order doesn't matter here, so we're just smushing them. Then over here, we're going to list anything that we haven't already written from B. Okay, so 2 was not included yet. We've got to put that on there. 4 wasn't either. 6 wasn't, but 7 was, so we won't list it again. Same thing with 8, already listed, and then ending with 10. So that would be our union of A and B. Then the second part wants the intersection, or where they overlap. Okay, so if we look at A and B together, we're looking for repeats. So that's the 7, that's the 8, and that is it for that one. So the elements in A union B, if you count them up, there are 10. But that's not the same thing as just adding the elements here to the elements here. Okay, that's because if you take these 6 and these 6 and add them up, you're really counting the 7 and 8 twice. So because there were repeats, we didn't actually have the same value as part C if we would do that. Now, if our sets were what's considered mutually exclusive, or if there wasn't an overlap, then we could go ahead and do that. Okay, but the formula that we're going to use generally is the one for non-mutually exclusive sets, and that is take the number in A, add it to the number in B, but then subtract off anything that shows up in both, because you counted them twice and we don't want to. All right, that's what we did here without a lot of work for part C, is just by listing it. Okay, so when you can list out your set and there aren't a whole lot of numbers, I encourage you to do it that way. Okay, this formula is useful when we have larger sets and we don't want to take the time to list stuff out. Second one, we're just going to practice a little bit more. This notation is slightly different because it wants us to find the probability. In order to do that, we must know the total. So they gave us our sample space. Okay, just some reminder vocab here. Sample space are all of the outcomes listed out. So our outcomes are 0 through 9, and it says A is 1, 3, 5, 6, 7, B is 2, 3, 5, 7, 9. So for A and B here, we can count because they have them listed out. So we've got 5 for this one, 5 over 10, reduced to 1/2. B, same thing, we can count. There's 5 there as well. So both of these are 1/2. Okay, these do add up to 1, but they are not complementary. Okay, so spending some time talking about vocab from last time. Okay, remember complements add up to 1, but the first rule is they must be mutually exclusive. Because these have an overlap, okay, as soon as I see that 3 shows up twice, they cannot be complements. Okay, this one, A intersect B, and we're going to go ahead and list out this set first, even though it's asking for the probability. The easiest way to calculate a probability is to list and count. So let's do that for this one. This means intersect or overlap. So we're looking at what number is shared by A and B. Okay, so it looks like the number 3 for sure, but also 5 and 7. So there are 3 total. We'll throw that over the total of 10. We can't reduce in this case, so we're just writing 3 over 10. When I ask you for probability on your homework, you can express it as a reduced fraction or a decimal. Okay, the reason I like fractions better is because they come out nice most of the time, whereas decimals aren't always the prettiest looking. If we look at this next one, it is asking for the union. Okay, what I want you to do is pause the video, see if you can write out what the union would be, and then go find the probability. Again, I like for these ones just to list out whatever comes first to start with. So I've got A first, just listing out, and then I'll tack on anything from B that hasn't been mentioned yet. So 2 hasn't been mentioned, but 3 and 5 have, 7 have. We just got to tack that 9 on. So 1, 2, 3, 4, 5, 6, 7 out of 10 for this one. These little hats that you see are the complements. Okay, so that says the complement of A, but usually I'll read it out loud as the probability of not A. And there's a really easy way to find this mathematically, but first I want to talk about sets, okay, because that's what we've been doing so far throughout here, is just listing out the set if it wasn't given to us. So when we think about not A, we are listing all the numbers that are not in A, but are in the sample space. So starting at 0, and then 1 was listed, okay, then 2, then 4, 5 and 6 and 7 are all there. We just have to end with 8 and 9. So there are 5 here. 5 out of 10 is 1/2. Okay, but another way you can think about this using the formula on your note card is if you want to find the probability of not A, because complements have to add up to 1, you can take 1 minus the probability of A. And because we had probability of A over here as 1/2, 1 minus 1/2 is super easy to take care of to get that a little faster. Okay, so let's use that on here. We've got 1 minus B we had over here was 1/2. So 1 minus 1/2 is 1/2 for this one as well. Okay, I'm going to have you add on just one example here to help you with your homework. We're going to find the probability of A intersect B complement. Okay, making sure we can do these same symbols when we had a complement involved, putting the couple ideas together. So because we didn't list out B complement here, that would be your first bet. Okay, any piece that is not written out in a set, you want to write out so you can look at it. I'm going to write it up here right next to A, just because that's what I'm supposed to compare for these. And B complement were the numbers that weren't in B. So that's 0, 1, 2 and 3 are there, 4 wasn't, 5 was, 6, and then 8 to finish up. So those are the 5 that actually were part of that probability. And we want to take A and find where it overlaps with that. So we've got an overlap of 1 for sure. And then if you look through here, the 6 also repeats. And it looks like that's it. Okay, so for those, we have 2 over 10, which would be 1/5 for the probability of that one. Okay, so just in case you see something with an intersection union that involves a complement. All right, we're going to review a couple Venn diagram problems. Okay, this is dealing with that formula that we talked about on the first example. Okay, we can find the union by adding the 2 and subtracting off the intersection. So the visual is supposed to help you without need of that formula, because usually when we can see something, the math is pretty straightforward dealing with addition and subtraction. So let's check out this one. We're supposed to draw a Venn diagram, and it says, in Animalville, you are only allowed to live there if you're single and own a dog, a cat, or both. So our bubbles are representing dog owners and cat owners, and because it can be both, they do overlap. Okay, so we're going to set this up, and it doesn't matter which side gets the dog, which side gets the cat. We just have to be careful when we go fill stuff in. So this first one, 185 people own a dog. So I'm saying in this full circle, 185 people exist. Okay, but some of them are in this moon shape over here that are only dogs, and some of them fall in the center part where you would own a dog and a cat. So distinguish on these ones, what I'm going to do is actually label outside the bubble and call that my 185. Then the second part, 120 own a cat, so similarly I would mark this as 120. And then 40 own both, that goes in my middle. Okay? And that lets me see really quickly, right here, 120, 40 of them are here, so there's 80 left to be only cat owners. On this side, 185 is my total, but 40 of them are here, so there's 145 left over to be just dog owners. We want to know how many people are in the town. Okay, so these requirements up here were important. You're only allowed to live in this town if you're single, meaning there's nobody sharing the same dog or cat. Okay, and you have to own a dog or a cat, so there's no one floating outside of these bubbles. So to find the total people, you just find the total of the three sections and add them together. Okay, and that gives you 265, and then we'll throw on a label of people. Okay, but I do want to show you how this relates to the formulas that you see on your note card. When we say this total people, we're really saying the union of the people who are dog owners with the people who are cat owners, because remember, union doesn't count the intersection twice. So on your note card, it says to calculate a union, and I'm going to use the letters that are given here. But to calculate the union, you take the number in the first set, add the number in the second set, but then subtract off the intersection. So for us, with numbers here, that looks like take the 185 you were given, take the 120 you were given, but subtract off 40 because you counted that 40 in both of those and you didn't want to. Okay, still coming up with the same answer. Okay, just wanted to show you there is another way to do that using your formula. All right, so the second part here is going to talk about the same Animalville, but this time it says currently 250 people live there, so it's not the same problem as before because that ended up being 265. But 120 people own a dog, 50 own both a dog and a cat. How many people own only a cat? Okay, I want you to draw this out with the information they give you and then see if you can answer that question. Okay, pause the video and take care of that for me. Same bubbles as last time, we're having dog and cat. For this one, 120 people exist in this whole bubble. 50 of them are in the middle. And then you can, of course, see that that would make 70 the dog-only people. But our job is to find this. And they also told us that the total has to equal 250. A couple different ways to do this. Okay, you can use the separate pieces here, but if you know that 120 are dog people and we're looking for only cats, really all you have to do is subtract off that 120 to get your 130 people. Okay. Same thing goes if you take your 70 and your 50, add them together, you still get 120, you're still subtracting. Doesn't matter how many steps you take, as long as you can come up with that answer for me. Alright, the stuff that's new for today deals with the multiplication counting principle, and we're going to do it by hand first time, and then we'll be able to see a pattern. So it says, it's a special day at the cafeteria, and you have, as a meal choice, steak or chicken for your entree, green beans or corn as the vegetable, and potato options of french fries or mashed potatoes. We're going to choose one entree, one vegetable, and one potato to make a meal. And based on that, we want to list out all of the different choices to come up with how many different options there are for these meals. So, setting out, we're going to write set brackets because sample spaces are always in a set brackets, and we're going to abbreviate here. Okay? It's really important when you're listing a sample space to stay organized. So what we're going to do is go through and take care of all of the meals that involve steak. Okay, so we're using S for steak, and then we're just going to pick a vegetable to start with. So I'm going to go with green beans and combine it with the different potato options. So steak, green bean, french fries, or steak, green beans with mashed potatoes. Okay, so that's taking care of steak with green beans. Now we're going to take care of steak with corn. Again, you could go with French fries, or you could go with your mashed potatoes. And keeping organized and following that pattern makes the second part super easy. If there were 4 choices to deal with steak, there should be 4 choices dealing with chicken. I've already used C through here for corn, so I'm going to use H for chicken. And then the pattern, green beans with French fries, then chicken, green beans with mashed potatoes, chicken, corn, French fries, chicken, corn, mashed potatoes, and there are 8 total meal choices. And that's fine as long as our choices don't increase. So what we want to do is be able to generalize about what's happening here. Okay, when we were going through here, what really we were doing was selecting one entree from the entrees listed, one vegetable from the vegetables listed, and one potato from the potatoes listed. So we've got 3 selections to be made. And because there were 2 choices for the entree, 2 choices for the potato, and 2 choices for the vegetable, what we ended up doing here is saying one choice and another choice and another choice, and is going to mean multiply for us. So we ended up with 2 times 2 times 2 to get that 8 choices. Alright, so when you are selecting any type of problem where there's just one from each group, you can use that same pattern. So here we've got 5 pairs of pants, 10 tops, and 4 pairs of shoes. We want to make an outfit of 1 pant, 1 top, 1 pair of shoes. But there are 5 different ways for the pants, 10 different ways for the tops, 4 different for the shoes, and all we have to do is multiply those together. So we've got 200 different outfits as long as they go together. Okay, that is the multiplication counting principle. Okay, but there's also something known as selection with replacement, or strings with replacement. And I'm going to skip over this theorem and actually show you an example first, and then it's going to make a lot of sense as to why it looks the way it does. So first up here it says, how many ways are there to answer a test having 4 true-false questions? We're going to set this up the same way we did the last one. Okay, we're making multiple selections and the pattern is the same, but the whole idea is we've got 4 questions that we have to make choices for. So first, second, third, fourth. But they're true-false questions, meaning I have 2 choices for that one. Okay, true or false. Okay, second question, I still have 2 choices, true or false, all the way through. But because these are the same types of questions, there's a pattern here that wasn't on the other one. Okay, I can generalize this as 2 repeated 4 times. And that's what this n to the k is saying up here. It says, let S be a set within elements, and there are n to the k possible strings with replacement of length k with elements from S. First of all, I want to talk about the word string. Okay, that word string is just an outcome. So when we're talking about this 2 to the 4, we get 16 total outcomes or total ways to answer this test. Okay, so a string would be one way to answer the test, like true, 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 true. Okay, but it says of length k, well, the true, 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 true was length 4. K really is talking about how many times you're repeating the selection. The number of elements is really how many choices you have. Okay, so this on your note card I think is written out this way, but let's go ahead and write it here. N is really your number of choices, and K is the number of times you repeat the choice. Alright, to finish this problem, it says if you guess on each question, what's the probability of answering all 4 correctly? Well, now I know my 16 is my total on the bottom. We just have to come up with what this all 4 correct would look like. Okay, when we think about answering questions. Okay, there's lots of different ways to do it when you're guessing, but of those lots of different ways, there's only one that's correct. When I'm filling out my answer keys, there's only one way to do it all right. Okay, so all right or all wrong, there's only one way. Okay, that's not true if you get like one wrong, because you could have the first one wrong, the second one wrong, the third one, or the fourth one wrong. Okay, but when it's all or none, it's exactly one way to do it. Okay, so let's check out this next one. It says there are 2 multiple choice parts to the mathematics section of the PSAT. So I'm going to go with part 1 here and part 2. It says one of them has 25 multiple choice questions with 5 options each, and the other has 15 multiple choice questions with 4 options each. Okay, so take a minute and go ahead and decide what each of the math there would be based on our new pattern. Okay, number of choices to the power being number of repeats. Okay, if we're thinking about this first part, 25 multiple choice questions with 5 options each really means like an A, B, C, D, E. So when you're answering your questions, we've got A, B, C, D, or E, 5 choices for the first one, 5 for the next, 5 for the next, and you would keep repeating that until you finished all 25 questions. So this would look like 5 to the 25th power. Over on the second part here, similar, we're looking at 4 options each though, so that's 4 times 4, 4, 4, all the way through. And this one only had 15 questions, so it was repeated 15 times. But these 2 things are part of the same test. We could write this 5 to the 25th because we're saying 5 times 5 times 5. You're answering the first question and the second question and the third. Well, similarly, we need to answer part 1 and part 2, so we're going to multiply in between. Okay, we know that with scientific notation, really big numbers come out. Okay, these problems are going to have big numbers with powers. Sometimes you'll get scientific notation like we do here. So go ahead and type in your 5 to the 25th, okay, then your times 4 to the 15th, and we're just going to check out the scientific notation. This one comes out pretty nice in general with scientific notation. If you can't avoid it, you can go ahead and round, and I really don't care what you round to. So 3.2 times 10 to the 26th power. We just have to know that this is talking about the ways to answer the test, so we do have to throw a label on there. That's it for that one. Alright, this one goes back to kind of a basic probability, but what we're going to talk about is more dealing with kind of our counting principle here, where we're not just making one selection. Okay, so we know with basic probability we need to know the total first. So it says in a bag there are 6 blue marbles, 8 red marbles, 6 green marbles, so we have a total of 20 marbles. Okay, so the first one says if Jeff draws out 3 marbles, replacing the marble after each draw, what is the probability they are all green? So we've got 3 choices here, and we want green, green, and green. Okay, but it says we're replacing the marble after each draw. Okay, that's important. We want to know our first probability, and that's 6 over our 20 of total. But after that 6 has been drawn out, they take the marble and they put it back in. So the second one is still 6 out of 20. And finally, the other one is 6 out of 20, okay, because they always put it back. So this kind of shows you that our power instances, just like last time we were working with our number of ways, it also applies to probability. So if you know the probability is the same each time, I'm going to go ahead and reduce this to 3 over 10, you can raise it to the power of how many times you're repeating the process. So this one was 3. And with this, you can type it in your calculator, but these ones are pretty easy to take care of. With fractions, you just take the power on the top and the bottom. 3 cubed is 27, and 10 cubed is 1,000. That can't reduce. There's your probability. Okay? If you want to write it as a decimal, again, I am okay with that. Part B, if he replaces the marble after each draw, so same process, it wants the probability of 2 red marbles, then a blue. Okay, so 2 red marbles. Again, if you can see that it's repeating the same thing, we can use powers to help us. Okay, red, though, is 8 out of 20. then we're doing again. And the last one is a blue marble, which is 6 out of 20. Okay, so what I was talking about with powers, if you wanted to write that as 8 over 20 or reducing that to 2 over 5 squared, you can. Okay, we still have to do the second part with 3 out of 10. Okay, but that is up to you entirely on how you want to handle that. We're going to simplify that. Again, you can throw the whole thing in your calculator. I do want to point out when you're typing stuff in your calculator, I'll show you on this one, and I'm going to use the not reduced version because, again, you don't have to simplify it all before you do this. When you're typing these in your calculator, you don't need parentheses. So if you want to type this in, you just do 8 divided by 20 times 8 divided by 20, and then times 6 over 20. Just change that thing to a fraction when you're done. So math, enter, enter. And then we've got our 12 over 25 to finish out with. And it looks like something, maybe I typed in wrong. Okay, yeah, I thought so. This should have been 250, which does reduce a little bit more. Okay, so 12 divided by 250, then your math, enter, enter. I missed the 0 there. And 6 over 125 is what I was looking for. What we want to do on part C is compare to what if we're not replacing it. Okay? Without replacement, I'm going to go back to this definition. Remember how this was strings with replacement? When it's not being replaced, powers cannot be used to simplify. You got to do each one separately. And the reason powers can't be used is the probability is going to change if you're removing marbles from the total. Okay, so if we look at part A, we still have our 3 green. That's what we're looking for. The first draw is not affected. Okay, but the second draw, I've taken out a green marble, so there are only 5, which means now I only have a total of 19. So my second probability would be 5 over 19. If I want to draw another one, I'd have to reduce both of those numbers again to 4 over 18. Okay, again, you don't have to reduce anything. In this case, not all of them do reduce, but just type that whole thing in your calculator. No parentheses are needed. And sometimes when you type these in, by the way, your calculator won't be able to change them to a fraction for you, so it'll be some sort of decimal forever. Like if I hit math, enter, enter, it would stay that, or scientific notation, again, when you hit math, enter, enter, it would say that. If that ever happens, what you'll want to do is actually reduce it first and then type it in, and then usually it can take care of it. Okay, so if you ever come out to a problem like that, that's what you'll need to do for me. Alright, last one here with the marbles. It says, Jeff drew 4 marbles from the bag without replacing them. What's the probability that the first was red, second was blue, and the last 2 were green? Okay, I want you to pause the video and try this one for me. Alright, this one. First one, no problem. Second one, third one, and fourth one. All of your totals are decreasing by 1. Okay, the first 2, the totals don't matter, but do be careful on this last one. When you're doing the second green, there's also 1 less green in the bag, so you have to decrease that top number as well. Final answer, 4 over 323. Last problem, the only reason it's on here really is to remind you of what a deck of cards looks like. Okay, so for those who are less familiar. But there are 52 cards, and they're split up into ace, 2 through 10, jack, queen, king. And these 13 cards happen for each of the 4 suits. So there are hearts, diamonds, spades, and clubs. Okay, so 13 times that 4 gets you to your 52. Now that we know that, we're going to follow the same process as last time. It says find the probability if you draw 2 cards without replacing them. Okay, so that means 52 for the first one and 51 for the second one. Then it said both cards will be hearts. Okay, so when we're thinking about hearts, we know the probability is 1 out of 4 suits, or that's 13 cards out of 52. And the reason I like the 13 over 52 is just for problems like this when we're decreasing, when it's without replacement. Okay, nothing wrong with you calling that 1 over 4. Second part then, because I've taken out one of these hearts, we only have 12 left. Okay, again, you're just throwing that in your calculator. I'm going to use the 1 over 4 because I know that's what that reduces to. And then that 12 over 51. Then math enter. We've got 1 over 17 for that one. Then it says what is the probability if you do replace the first card. So that's our 13 over 52 replacement. Remember, you can use powers if it's helpful. Okay, I think it's helpful for this one because I know it's 1/4 squared, which is 1 over 16. Okay, so when you're putting the card back, you're a little bit more likely to get that second heart. If you have any questions while you're working on your homework, because there are a couple tricky ones there, please feel free to stop by and come ask some questions.